Okay, welcome to Lesson 22. We're going to talk about quantized electric and magnetic fields today and spontaneous transitions. So, let's start by discussing what happens if I have a box with only one mode of radiation. And let's just remind ourselves about Maxwell's equations that relate to the electric and magnetic fields. There are basically two of them we're going to be dealing with today. And we're going to be talking about regions where there is very little charge. So we're going to ignore. So we're going to talk about the effects of putting charges in here as a perturbation. So we're going to quantize the fields, assuming that there are no other charges. So that means in the curl of B Maxwell equation, there is a term that has to do with the current, but there's not going to be any free charge. And also the divergence of E and the divergence of B we're going to assume are both zero, since there's no free charges anywhere. Under those circumstances, if you wrap these guys around each other, you'll find that you get a wave equation, and the wave equation has solutions which, in the spatial part at least, go like the sine and the cosine of kz, where k is a number that is set up to satisfy the boundary conditions, and in this case the boundary conditions are going to be that the electric field goes to zero at the ends of the cavity. So we can assume the cavity has conducting walls or something. And let's remind ourselves how the curl works. Curl is a vector operator that acts on a vector field, and in this case, if you apply it to a field that only has an x component and it only depends on z, so the only thing that's going to matter is the ddz part of Ex, and if you work that out, it turns out to be Dex dz j hat. So that's the part that matters. Remember that the middle column, and you do a determinant, the middle column gets a minus sign, but then the ddz also gets a minus sign, and those two minus signs cancel out, and you end up with positive Dex dz. And the thing points in the j hat direction. But of course, if you evaluate that, you notice that you go from sine to cosine. So at least the spatial part of B, because the curl of E has to equal minus the rate of change of B, the spatial part of B has to go like cosine. So that's something worth remembering. And then let's also go ahead and evaluate dE dt. I'm going to assume that the time dependence of the field is proportional to this thing I'm going to call Q. Q is just some function of time, classically. Well, I don't know what it is yet. I'm going to work it out. But I want it to have units of length. So what I've done is to divide Q sub n, which would be the nth mode. That n is the nth mode. So Q sub n is going to be divided by some length parameter. Now, it's not necessarily the length of the cavity. It's just something that has dimensions of unit of length that makes the dimensions of this thing work out. E0 is some base electric field amplitude. Q is some like a Fourier coefficient, but it depends on time, and it has units of length. And then the L is just some parameter that has units of length, which will work out later. Okay, it's going to end up going away, but we'll see how that happens. So let's go ahead and look at the second of Maxwell's equations. The curl of B is related to the time rate of change of E. Now we know that the spatial dependence of B has to go like cosine, so that the curl of E equation works out to be minus dB dt. But I've come up with a new time-dependent function for B, which I'm going to call P. The reason I'm calling them Q and P will become clear momentarily. But P is going to have units of momentum. So to make it have units of momentum, in order for the units of this whole expression to work out, I need to divide by something with units of momentum. And so I'm going to divide by a mass times a frequency times the same length parameter that I had in the other equation. And at this moment, I'm not going to explore what those actually mean, but they're just letters, basically, that scale the magnetic field. Again, the curl of B is expressed in this way, and it works out to be minus dB dz times I hat. Of course, dB dz is related to the cosine. If I take the derivative of cosine, I get minus sign, and the minus dB dz and the minus sign cancel, and I end up with a plus sine function. And I get out, of course, a factor of k sub n because I've taken the derivative with respect to z. Also, taking the time derivative of b, you notice I get a p dot. That's basically it. And now let's rewrite those two Maxwell's equations in terms of the results we just cooked up, and I get these monstrosities. But you'll notice a bunch of stuff is going to cancel out. So for example, you notice that the L's go away, and the cosines and the sines go away, and what I'm left with is a couple of equations that relate the Q's and the P's. Now, we know from studying electricity and magnetism that if I've got an electromagnetic wave in a cavity, that the electric and magnetic fields are connected to one another, and they're proportional to one another in a sense. And so I'm going to put in that proportionality. I'm going to put in that B naught is equal to E naught divided by C. And I'm going to put in that C is omega divided by K. These are just the definitions of C and K and omega. And if I do that, an interesting thing happens. These two equations, which look so hideous, the E naughts end up canceling because of this substitution, and some of the other things go away, and I get two equations. I get that P is mq dot, and P dot is minus m omega squared q. Well, the first equation is just the definition of momentum, mass times the rate of change of position. If I think of Q as kind of like a position thing, and P is like a momentum thing, then P equals mq dot is just the relationship between the derivative of position and the momentum. And the next equation is basically Newton's second law for a simple harmonic oscillator. P dot is minus kq. K is m omega squared. So, and don't confuse the spring constant k with the wave number k sub n. Those are not the same thing. M omega squared is the same as like a spring constant. It's a restoring force. So what we find is that the equations of Maxwell, which are electromagnetic field equations, can be mapped onto the simple harmonic oscillator through this sort of bizarre parameterization. But that's useful. So SHO, simple harmonic oscillator, that's useful because we know how to quantize the simple harmonic oscillator, and the procedure is exactly the same. We know that Q and P are non-compatible observables that have a non-zero commutator. We know that the Hamiltonian can be expressed in terms of the fields. Let's go ahead and do that. Let's plug in our definitions of the fields. We stick those guys in there. We make our substitutions. We integrate over the size of the cavity. We get the volume of the cavity now appears here, and if I make the substitution that E naught looks like this, in other words, I've just defined E naught to be this. Again, I want you to suspend your disbelief for a moment to see where this is going. But if I define E naught to just be a magnitude of electric field that's expressed in this way, then this equation for the Hamiltonian reduces to this. But that's just the Hamiltonian for the simple harmonic oscillator. And we know the simple harmonic oscillator already has a length parameter. It's the oscillator length. And we can express Q and P operators for the simple harmonic oscillator in terms of raising and lowering operators. A plus and A minus is what Griffiths uses. The rest of the world uses A and A dagger. So I'm going to switch to the notation of the rest of the world, since none of this material is basically in Griffiths. So A dagger is the same thing as A plus, and A, without any notation, is the same thing as Griffiths A minus. If I plug those two definitions for Q and P into the Hamiltonian, I get the following result, which is that the Hamiltonian is h bar omega times A dagger times A plus a half. And you know A dagger times A is nothing other than the number operator. It measures the number of a pure quantum state and an eigenstate of the Hamiltonian. And so this just says that h bar omega times the quantity n plus a half. Okay, now let's take that. In order to make this all work out, I had to assume E naught was equal to this bizarre expression. Let's plug that back in. Plug that back into our field, and then put all this stuff together. We'll put in the operator for Q. We'll put in this square root goober thing for E naught, and we'll go ahead and plug that into the formula for the field. And let's see what all comes out. Notice some stuff cancels. The L squared in the numerator of the E naught expression and the L in the denominator of the electric field expression cancel. So this length parameter that I introduced just to keep the unit straight ends up canceling in the end. And when the smoke clears, what I get is an expression for the electric field that depends on the raising and lowering operators. The quantum mechanical version of the electric field, once I've quantized the simple harmonic oscillator version of Maxwell's equations, turns out to look like a displacement. It looks a lot like the displacement operator for the one-dimensional simple harmonic oscillator, except that it's got this square root of h bar omega over epsilon 0 v. Notice that when you square the real electric field, the classical electric field, you get an energy density if you multiply by E naught. And notice if you square this and multiply by E naught, you get h bar omega, which is an energy, divided by volume, so you get an energy density. And it's the right thing to put in front if you want to think of one photon being confined, one photon of energy h bar omega being confined to the volume v. So it's kind of a rough concept, but at least it gives you some intuition as to why that factor needs to be what it is. And let's talk about the consequences of this. Of course, you could also make up a similar expression for the magnetic field, but because the transitions we're interested in are primarily related to the electric field, the dipole transitions, I'm not going to worry about that. You could, of course, do it. Just do exactly the same thing I did with the electric field, but for the magnetic field, using the P operator. So let's talk about stimulated transitions. If I have an initial state where an atom is in an excited state, E, and we're talking about a single mode, that it's in a cavity with a single mode that has n photons in it. That'll be n. So this expression, the first thing is the atom's quantum state, and the second thing is the electromagnetic field's quantum state. And the final state is going to be the atom is in the ground state, and the electromagnetic field now has n plus 1 photons in it. Can I use perturbation theory to look at this? And the answer is yeah, I can. Let's imagine the interaction is the same interaction we've talked about in the past, where the electric field gets dotted into the dipole moment. The energy is really minus the electric field dotted into the dipole moment, but remember the charge on the electron is negative, and so it works out to be equal to the magnitude of the charge on the electron times the x. Now remember, our electric field only has an x component, so when we take the vector electric field and dot it into the position vector, we just get the x component of the field, which is just E, and the x component of r, which is just x. So that's why we have a scalar here of the interaction energy. And I want to write, just like we did last time, I want to write the quantum state as a superposition of the initial state and the final state with a time-dependent coefficient out in front. And then now basically the math is identical to what we did last time. We can write out the time derivative of the ground state amplitude. It's proportional to the amplitude of the excited state, and then it's the matrix element between the initial and the final state, and then it's this time exponential with the difference in frequency between the initial and final situation. Notice there's no classical field here. The only field is the quantized field of the cavity with n photons in it. And the perturbation is actually a constant perturbation. So kind of interesting. If we use the same trick we used last time, we can put in what the interaction Hamiltonian is. We get one term that looks like GXE, that's the dipole moment evaluated between the two states, the ground state and the excited state. And we get the electric field operator acting on the n photon state and taking the n plus 1 photon state inner product with that. And notice that A is not going to contribute, but A dagger does, because A dagger takes n photons, bumps it up to n plus 1 photons, and gives us a square root of n plus 1. The other thing is, I'm assuming the atom is in the center, where the sign of KNX is 1, or it's a sign of KNZ is 1. I'm putting the atom at a maximum location of the electric field. If you move the atom around, depending on where it is, you might not be in such a place. In a very large cavity with walls that are very far away, many, many wavelengths away, this isn't going to be a big factor. What you can do then is, instead of dealing with standing waves, you can switch to traveling wave representation. But it doesn't make any difference in the end, so we'll just assume the atom's at the center. Let's go ahead and evaluate those matrix elements. The GXE, I'm going to call that DEG. That's the dipole moment taken between the states E and G, or the expectation value of position taken between the states E and G. And then, of course, the electric field matrix element turned out to be the square root of n plus 1, just like it is for the simple harmonic oscillator. Now we can integrate that, assuming that the excited state n amplitude at t equals 0 is 1, just like we did before. And we go ahead and perform the integral, and what we get is that we have a sine delta t over 2 divided by delta. Notice that there's a square root of n plus 1 there. What if the field contains 0 photons initially? Well, classically, nothing would happen, because there's no field there. But because that's a square root of n plus 1, you'd still get something, and that square root of n plus 1 is the reason why spontaneous transitions occur, because the field has some non-zero n equals 0 value, or n equals 0 fluctuation, and that causes stimulated emission with no photons. So that's what we wind up with. We can replace the square root of n plus 1 with 1 if n equals 0, and we still get something. Let's go ahead and talk about what happens if I have more modes. All this has been done assuming a single mode, but of course in a real big box there's going to be many, many modes, and this is one of the reasons why the exact location of the atom doesn't really matter very much, because when you add up all those different modes, you're going to get some. And so let's go ahead and talk about it. Now we have a wave function which is no longer just two components, but now it's got many, many components. It's got, for every mode in the box, there'll be a number of photons in mode 1, a number of photons in mode 2, a number of photons in mode 3, and the atom can be in different states, call those states J. So we'll need a coefficient that depends on time for every possible state that's interesting of the atom, plus every possible number of photons that could exist in each of the very many different modes. So n1 could be 0, 1, 2, 3, 4, n2 could be 0, 1, 2, 3, 4, and so on. So this is a very large space of states, and the question is, what happens when we repeat the same procedure? We can basically go through the same process, but what we need to do is to calculate the probability of each of these different modes for being populated, and that's going to depend on the number of photons in the modes to begin with, and the number of photons we're interested in being in the modes at the end. And it's a generally fairly challenging problem, but if we assume that the system starts out with the atom in the excited state and no photons in any of the modes, then the final state is going to be the atom in the ground state and one photon in one of the modes, and then another state will be a photon in another mode and a photon in another mode. So what we end up having to do is to calculate the probability of a photon being in any one of those modes, but we have to add the probabilities up for all the different modes. So basically we take the expression at the top of the screen and add it up, square it first to calculate a probability, and then add it up for all the different modes. That's not that bad. One of the things we have to do is to go back into the mode counting business, which is exactly the same as it was when we dealt with electrons, fermions in solids, or if you've ever talked about black body radiation, it's the same business. We can switch from K space to omega space. There's not that big a difference between the two. For every K, there's an omega. And omega is just about the energy, and K is just about the momentum, but they're still directly related to one another. And then we can convert this sum over modes into an integral. Now here's the thing. The integral is very sharply peaked around omega 0 because of the way the sinc function gets so narrow so quickly. We don't have to worry about the fact that there's an omega squared in the density of states, because omega squared varies very slowly, and the sine function is very sharply peaked. It's a sinc function, really. And if we make the substitution that delta omega, or delta t over 2 is equal to x, and integrate, we find that that integral in a very short period of time reduces to pi times t over 2. So it's just an integral proportional to time. And if I plug that back in, I get an expression for the probability of the thing jumping to the ground state. I've added up all the probabilities of going into all these different electromagnetic modes of the box. One thing I didn't do was to be careful with the polarization. It turns out if you are careful with the polarization, there's a factor that comes in, and you end up with a 3 pi downstairs here. But and you can see Griffiths actually deals with this when he talks about stimulated emission, and you can look at his equations to deal with that. Basically, you average the dipole moment over all the different directions that the thing can go, and you get this factor of 1/3 is what it boils down to. And what I want to focus on is the fact that this probability is proportional to time. So that means that as time goes on, the probability of being in the ground state grows. But of course, that means the probability of being in the excited state has to diminish. So we can actually improve our situation by taking that into account. We're going to define the rate of transition from the excited state to the ground state as this expression divided by, it's the probability per unit time. Now, the probability expression is only valid for short periods of time. But what we can do is say, look, if the probability of getting into the ground state has a certain rate, that means it's going to bleed the excited state of probability at the same rate. And what we end up with is it's almost like discharging a capacitor. As you discharge the capacitor, the current drops because the voltage drops, and then the rate at which it discharges drops, and it's basically the same math. You can approximate the rate of change of the amplitude to be in the excited state as half. Remember, it's got to be a half because the amplitude goes, the probability goes like amplitude squared, and so that gives you a differential equation to get the amplitude to be in the excited state. You can then plug that amplitude back in to the perturbation expansion and use it to correct for the time-varying amplitude of the excited state, and you get a differential equation that looks like this. But notice now there's an imaginary part and a real part in the exponential. And the short story is that when you grind through all of that and work out the answer, you end up with an extra factor in front of the probability, and it has to do with the rate at which the thing is losing probability in the excited state. In other words, the distribution of energies in these modes in the box gets spread out, and it gets spread out by an amount that's proportional to the rate at which the excited state is being drained. And that's the idea. We're going to need this because this is critical to understand laser cooling, and that's going to be our next subject. Talk to you soon.